right, so we've got a closed rigid tank. It's filled with water. Initially at the critical point, the water is cooled until it attains a temperature of 400 degrees Celsius. We want to show the process on a TV diagram and figure out what the heat transfer is in BTU per pound mass to or from the water, and we're told that there's no work done on the water. So I've got all my given, my find, at least for the heat transfer, and we'll handle the TV diagram in a second. And then I'll put in the assumptions that we need to make as we go along in the problem. So let's see, first thing that I need to do is figure out what do I mean by that critical point. Well, you can figure out the critical point for any substance in table A1 or A1E, and it's unique for whatever substance that you have. So for water, it's 1165 degrees Rankine, and the critical pressure is 218 atm. So what that critical temperature and pressure are, it's the point at the very top of that liquid vapor dome. All those properties can be found in your at the very bottom of your table A2, which is the saturated tables that are organized by temperature, or you can find them in table A3E. So we are at the critical temperature, so 705.4, and of course the corresponding critical pressure is 3204 psi. And you'll notice that the V sub F and the V sub G values are equal to one another here. Same thing for our internal energy. So with that in mind, let's go ahead and figure out what our heat transfer is. So in order to do that, you need to apply your first law. And it's a closed system. All indication is that this is a sealed system. It point blank says that it's a closed rigid tank, so closed, sealed. And so my first law for a closed system is Q minus W equals delta U plus delta kinetic energy plus delta potential energy. And I'm going to go ahead and assume that kinetic and potential energy changes are negligible. There's nobody picking this tank up or moving it around, so I can go ahead and ignore that. And I'm told point blank that the work is equal to 0, so everything boils down to Q equals delta big U. And I'm going to put that in terms of delta little u. So big U would be in terms of BTU, little u would be in terms of BTU per pound mass. And then if I divide through by the mass, I get things in terms of little q. So delta U is U2 minus U1, and now I just need to go through and solve for each one of my states. So it's state 1. I know I'm right at that critical temperature and thus critical pressure. I'm right up there at that temperature and pressure correspond to one another. So if you're at the critical temperature, you're also at the critical pressure. So at that critical temperature and pressure, my internal energy, U sub F and U sub F and U sub G are exactly the same. So the internal energy is just 872.6 BTU per pound mass. And now I need to go to state 2 and figure out what I know there. So I know the temperature is 400 degrees Celsius, but I need some other independent intensive property to figure out the state of my system. And it looks like since I've got a closed rigid tank, I can say that the volume is constant, and I've got a closed system, the mass is constant, and therefore my specific volume is constant as well. So with that in mind, I need to go back up to state 1 and figure out what that specific volume is. And you can see at the critical pressure, it's unique in that the V sub F and the V sub G value are equal to one another, and I just need to pull that off the table. And then going back to state 2, I need to figure out what state I'm in. Am I saturated? Am I compressed? Am I superheated? Probably not superheated because it tells me that I'm cooling things. So if I start off at the top of the dome, I'm probably going to go down, right? Go down in temperature and go into that two-phase region, or maybe the compressed region. Well, actually, it'll be the two-phase region because the specific volume is constant if you think about the direction of the TV diagram. But anyway, but I can see at 400 degrees Celsius and a specific volume of 0.05053 feet cubed per pound mass, I can see that I am two-phase. I'm between the V sub F and the V sub G value. And so if I calculate what my internal energy is based off of the quality, I can see that I can pull off the U sub F and the U sub G values off the table, but I do need to calculate the quality, and I can use my specific volume to do that. Remember, your specific volume, V2, is also equal to V1, 0.05053 feet cubed per pound mass. And if I plug in all the numbers, I just solve for my quality, plug in my numbers, I get a quality of 0.0173. And then if I plug things in, I get an internal energy of 397.7 BTU per pound mass. So ready to plug things in, and I end up getting a heat transfer of negative 485.5 BTU per pound mass. So that negative sign indicates that heat is leaving the system, and that makes sense given the wording in my problem. It says that things are cooled, so you would expect, right, the heat transfer is going out of my system. And then I did need to draw things on a TV diagram. So this is what I was talking about before. You could sort of visualize that you were going to be in the two-phase region, because you start right up there on the top of that liquid vapor dome at the critical point, and your specific volume is constant, so it's going to go straight down, and it's going to cool down to 400 degrees Celsius. All right, well, I hope that was helpful. Thank you very much for watching.